Hello, everybody. So today's session, I decided to call from novice to data ninja because the plan is to learn a lot of different data tricks that you can hopefully use in your own work. And the reason for this tutorial is that I've seen a lot of tutorials which are Python and time series analysis, Python and image processing, Python and networks. But okay, you have to go to all these tutorials separately, and sometimes you just don't have the time. Or sometimes you think you don't need it, so that's why you don't go. So my thinking is you never know what you're gonna need. So the idea is within 2 hours to try to go to different data and how we can use it in Python, so that kind of you get prepared, at least know where to start in the future. So that's kind of the plan for today. And today we have several notebooks that we will use. And in order to get those notebooks, you can go to the following address, which I'll put in a second. So this is, can you see in the back? Let me try to make it bigger. I don't know if I... Okay, I made bigger, the address doesn't become bigger. Well, let me try to do that. So this is the address of the repository where I have stored the materials. So if you have GitHub installed, you can go and clone this repository and directly work from it. If you don't, you can go to the website and click on a download button somewhere. Clone or download. So basically, if you've already used GitHub, you know how to do it most probably. If you haven't used GitHub, you can just download the whole folder, and you're going to have several notebooks inside this folder, and you'll be able to use them for your work. So does this make sense? And then you can kind of follow together with me. You don't have to really set up everything, but if you want to play with the notebooks, it's better to get them for yourself. So apart from the actual repository, we'll be using a few data sets. So there are links here to a sound data set and a video data set. So you can download them now, or you can wait later when we reach to them. Then you can go and download them when you need them. And you can put them in a folder called data that I have here. And if you want to look at the link, here it is again. So people are getting these materials, okay? Okay, I'll start talking, and in the meantime, you can kind of finish up getting things. And please, if you have any questions, let me know. So basically, in order to start working with these notebooks, I assume you have a little bit Python knowledge, in the sense that, or knowledge from another programming language, in the sense that you most probably have already Python installed, and I assume that you have installed like Anaconda Python, but most probably it's going to work with another version. You just need to change a few things maybe. And in general, I assume you already used a Python notebook. If you haven't, it's pretty easy. You just you open a terminal. I'm kind of cutting this out. it got stuck. So basically, you can run from the terminal Jupyter Notebook, and you're gonna get the notebooks open. Have people used, so just to get an idea, have people used Python before? Okay, all right. So yeah, if you haven't, I think still you can kind of look at the libraries and follow the talk independently. Yes?
Can you make the terminal font bigger?
Yeah, it kind of got stuck, so it's not useful right now. Anyway, I'll open another window. And I want to make this bigger. So from the terminal, you just run Jupyter Notebook. And that opens like a browser. And from the browser, you can go ahead and we'll start with the spatial network notebook. So basically, you click on it, and you can start using it. And you can basically click on every cell and run the cell with Shift and Enter. So pretty much that's it. So the first topic is spatial networks. And do you want me to make this bigger for the people in the back? I'll try to make it a little bit bigger. Is that okay? So basically, we have a few simple goals for the first part. Is that we're going to learn how to deal with data that's spatial, and we're going to build some sort of network for this data, and we're going to visualize the data and the network, and we're going to learn some features for this data set from the network. So that's kind of the goal. So basically, simple introduction to dealing with spatial data and networks. Okay, so the first part is just to load a few packages that are very common. So these are Matplotlib, NumPy, Pandas. These are packages that are used almost every time, nothing special. And then we will go and get a data set, which is in the data folder of this repository. And the name of this data set is statecapitals.csv. So this data set, you can actually look at it from the data folder. So it's just a text file. And what it contains is the state capital, and the latitude and longitude. So very simple data set, very small data set. So we are going to read this data set in Python. And in order to do that, we're going to use a function from the Pandas library. So it's read CSV function. And when we do that step, we basically have the data set stored in the data variable. So we can kind of have a look at what's inside from Python. So we see that we have 4 columns with the names and the coordinates. And that's in general how you read CSV files. So next, let's try to plot this data on the, so that we visualize it. Pretty much all we need to do is take these coordinates, the longitude and latitude, and treat them as x and y coordinates, and plot them on a simple plot. So this is not a map. I'm just plotting them as points in R2. Okay, so this just gives us like a sort of an outline of the country, and we see that there's like there is Alaska and Hawaii, and basically we see that there is some structure in this with these points, and we can say that there's maybe some connectivity, right? Like based on, like if we set some boundaries, we can say that some nodes are closer and some are further away. So in order to do that, so the next kind of exercise is that we're going to calculate the distance between every 2 points in this data set, and we're going to build a graph from this distance. So this is kind of true in general. If you have spatial data, you can actually build a graph using the distance between the points. So how do we calculate distances between points? Can somebody volunteer to say in general? We have latitudes and longitudes of these points. How do we calculate the distance? So I heard great circle somewhere. So yeah, we cannot just do Euclidean distance. We need to kind of walk along the circle because the Earth is round. And technically, the Earth is not even a sphere. So there's like it's geoid, so it depends where you are. But for the sake of this tutorial, we'll assume that it's a sphere, and we'll approximate the distance by walking on a great circle. So how do we do that? Well, there is actually a formula for that. So the main point is just to use the formula, and it's called the Haversine formula. It's one way to do that. There are more precise formulas, but the idea is that every time you get some sort of geographic coordinates, you have to use this formula to calculate distances. And I'm not going to get into the details of the formula. You can kind of review it, but it's a bunch of sines and cosines and so on. And you have to convert the latitude and longitude to radians first and then do the calculation. So once you have that, you actually have the correct distance. So as I say, in the next step, basically, I create a little function which is called spherical distance, and I pretty much do all these calculations of sines and cosines and so on. And I use the radius to adjust for the radius of the Earth, and I get my little function to calculate distances between 2 points. And I test this function. So in order to test it, I need to extract 2 sets of coordinates, and because we got the data into this pandas data frame, it's kind of a little bit irritating to work with it, but okay, this specifies that I want to get the columns, latitude and longitude, and this ilog thing just indicates that I want the first variable and the second one. So I just took the first and the second one row, but there's better ways to do it. You can use the name of the city to calculate this if you want to know the distance between 2 cities. So yeah, we can calculate this, and it gives us some number, and this number is in kilometers. And this is one of the biggest numbers because I think the second one was Alaska, so the distance is bigger. Okay, so basically now we have this function. It works for 2 points, but we want to, yes?
Why have you used log instead of ilog as the second argument?
If I wanted to use log, I should specify the name of the index. So that's the difference between.
Exactly. So in the second argument you use log.
Oh, that's a mistake. I should be consistent. Yeah, that's. In this case, they're both. I think the index is the same as the number, so it doesn't matter. But yeah, that should be consistent. I think in this case it's just because the index is just, the name of the index is 0, 1, 2. So it's pretty much the same whether you use log or ilog. Just to clarify, if I had some names here, like I had actual names of cities as an index, then it's better to use log. But because I have numbers, it's the same with the index location and the location of the name. So this is like a detail about data frames and how you have their indices. Yeah, I think the right way to do it is, if we really cared, we should have made this column maybe be the index, and then we can use the names to compare distances, or even the state, so that it's more explanatory. Okay, so anyway, this is just an example between 2 points, and we need to do it between all the pairs, right? So how do we do that in general? How would you go about calculating distance between pairs of points? How would you write your own program to do that? Any ideas? What's the simplest way to do that? We have one set of points, another set of points. How would you implement this in any language? Couple of loops, yeah. So that's kind of one of the, if you're not, if it's the first thing to do just to get it work, that's what I would do. And in general, that's it's kind of like, it's considered an inefficient way. So for such a small data set, it doesn't matter. But when you have a lot of points, you actually don't have to go through the 2 loops, because the distance between A and B is the same as the distance between B and A. So there's kind of efficient ways to go through pairs of points. And that's why there is this function, which is part of the SciPy package. So we can run it here. So this function is called pdist, which is pretty much stays for pairwise distances. And in general, if you don't have anything here, it's going to calculate Euclidean distances. And the nice thing about it is that under the hood, they thought of the best way to kind of calculate these distances. So I don't think they have 2 loops. I think they're more efficient data structures to deal with this problem. So we just use their function because they thought already about it. And instead of using a standard distance, which would be if we don't have anything here, we put our function. So basically we substitute our own function. Okay, so now we can actually have, we can run that. And we see that when we run this pdist function, what we get is we get some object that is just a vector. So basically we get like a list of distances. While what we want is, I want to know what's the distance between I and j, right? So basically what this function is returning only half of, like if we think of the distance to be between every pair of points to be like a matrix, it only returns half of these values, because it's more efficient, right? It doesn't need to store the other half because they're the same. But it's not so it's a little bit hard to say which distance is what, right? Because they're just a long list. I mean, they're ordered, but it's not that intuitive. So you can always go back to the square matrix, and for that you can use this function which is called square form. So it comes again from this distance module in SciPy. So when we do that, we run that and we see that the shape, something went wrong. Okay, let's rerun this. So the shape now is square, 50-50. Okay, does it make sense? Pretty much. The first thing contained half of the values in this square matrix and in a list. Now we have a square matrix, so we can say ij corresponds to this distance. Okay, so this is how to get distances. The next step is to create a network out of these distances. So how do we do that? Well, we have to define what we mean by a network. And in this case, I decided to define that any 2 points would be connected if their distance is less than 300 kilometers. So basically, I define what my network is. And when I basically, if I set this distance less than 300, I get a matrix of zeros and ones, and which says whether 2 cities are connected or are not connected. And that matrix is very important in general anytime you work with networks, because that matrix contains all the information about the network, because it tells us that 2 nodes are connected or 2 nodes are not connected. So basically it describes the structure of the network. And it's called adjacency matrix. Okay, so we have this matrix A, and now that we have it, we can kind of dive into the Python package which deals with networks so that we can kind of visualize the network. So the package in Python for networks is called network X. Of course, there are other packages, but this is one of the standard ones. And the standard way to import it is with this abbreviation NX. And then because we want to build the network from this matrix, we use this function from NumPy matrix to create a graph. So basically, I need to run this before that. So basically, it created some object which is called G, and this object is of type graph, so it's a special object. But the important thing is that it contains the nodes, which here are just numbered from 0 to 50, and it also contains the edges. So basically it tells us if 2 nodes are connected, so it stores the edge. So basically from the matrix form, it stores the matrix in this node edge way. Okay, so let's look at it. So in order to look at it, we use this draw function, and it just draws the network. Okay, so that's what we get. Does anybody have explanation of why we get that, and what does that mean? Or does it mean something at all? So basically, what is a network? A network just tells that things are connected or not connected, and we didn't even put any weights. We just said 1 or 0, right? Connected, not connected. So in some sense, this is correct because it put all the nodes and it connected the right ones. There's nothing wrong. And the idea is that it arranged them this way. It's because in the network, there is nothing about the distances, right? It's nothing about the geographic information. So pretty much, Python is free to arrange these nodes the way it likes. And this layout is some standard, I think, some sort of circular layout. So there's nothing wrong with that, although it doesn't look like we expected it, but it's not wrong. But if we want to put more structure, then we can just add an extra step, and as an extra parameter here, we can add the longitudes and the latitudes. So pretty much you specify the layout, and we can look at it this way. Okay, so now they are at least in the right location. They're not very visible, so that's why I added a few more steps. So I made the node size 20 and the node color blue for difference. You get a more clear image of where the connections are. So, and then you can play further on, you can add titles and so on. But basically, this is the way you visualize a network. Okay, so we have the network, and as I said, I want to kind of learn something about this data set from the network. So not from the data directly, but somehow through the network. So as I said, the adjacency matrix describes the whole network, the whole graph in some sense. So pretty much we can do things with the matrix itself and get things about the data set. So what can we learn? Well, one of the popular properties for a node of a network is the degree, and this is the number of edges that you have from a node. So okay, so we can actually calculate it from the adjacency matrix, because each row tells us how many connections this node has. So if we sum all the values along that row, we get the degree of the node. Does that make sense? A little bit of algebra, but the point is that we can get information. So we can basically get the degree of each node, and here we get the numbers, and we can build a diagonal matrix out of it, and because we'll use it in a second, so it's called the degree matrix. Okay, so there is another matrix that's very useful, and it's called the Laplacian matrix. And that matrix is simply we get the degree matrix and subtract the adjacency matrix. So just some matrix doesn't mean much, but it actually has a lot of interesting properties. So one of them is that if we calculate the eigenvalues of this matrix, we'll get information about the number of connected components. So from some algebraic property, we get some sort of geometric property. So let's do that. So let's calculate this matrix, because I believe it's useful. And then we're gonna calculate the eigenvalues and the eigenvectors. For that, we can use the SciPy linear algebra package. And we just calculate eigenvalues, eigenvectors, and then we're going to plot them, okay? And I learned, actually, I kind of didn't realize that they don't come ordered, so I had to sort them so that they are ordered. I guess I expected them ordered, but anyway, we can sort them and plot them. So you see that there are a lot of them which are 0, and a lot of them come kind of in a chunk together, sort of, and then some of them are separate. Okay, so the ones that are 0, basically we need to count how many of those are there, and I counted them already. They're like 22, and that tells us that basically that the null space of this matrix is 22, which on the other hand means that we have, I think we have, yeah, we have like 22 connected components based on that, okay? So let's look whether that's correct. I mean, this is just from the properties. So let's look at this. So you can see that there are only a few bigger components, but each one of them, each of these guys is connected to itself, so it's also a connected component. So that's why if we count all of them plus the few chunks, like they're like 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 chunks and all the single ones, and you'll see that it's like 22. So kind of like you can, so for this one, it's easy to count them. If I have a network of million nodes, I don't want to count them by looking at them. So then you can just use this matrix to calculate the number of connected components. Okay? So these are just kind of nice, interesting things. What else can we get from this matrix? There's some other properties, and I won't get into them. But you can kind of look at other eigenvalues and get something that's called like algebraic connectivity, which tells you how connected the network is and so on. So basically you get other properties. So in some sense it starts to look like you learn about clusters in this network. Okay, so, and just one final note is that for this example, I assume that the network, the adjacency consists of zeros and ones. So pretty much I have edge or no edge. If I actually took the distance and set that distance to be the weight of the edge instead of having cutoff, because I decided like, I arbitrarily decided that less than 300 kilometers is the cutoff, right? But I don't have to do that. So basically, I can leave the distance as it is. It's going to be my weight. And I can kind of do the same steps like getting the Laplacian and so on. And the properties of the Laplacian would correspond to some sort of clusters in this network. So there's not going to be a sharp cutoff like here. Here is just number of connected components. There you kind of look at the eigenvalues and look at for a cutoff. And you can say more or less, okay, this is the number of clusters. So it's a very nice feature when you work with spatial data. So pretty much when you have time, you can kind of, you can actually redo this example with the distances, not with the zeros and ones. And you see that you get some interesting information. Okay, so this is kind of this is what I wanted to share with you on networks. Do you have any questions regarding this topic in general, like how to go further from this point? So there's a lot of kind of like properties that you can kind of start calculating later on. So they have names. I mean, it's kind of like you have to dig into the literature. But the idea is that once you can plot, kind of visualize them, compute these matrices that are important, you have everything you need. Oh, and regarding like kind of working with larger networks, in that case, usually it's not good to work with the matrices. The way we kind of did the algebra here, it was pretty nice. But for large networks, that's pretty expensive. So if you work with the matrix, make sure that you store it as a sparse matrix, because then you just store the edges that you have. You don't store things that are zero. Or even further, you might kind of abolish the whole matrix thing, although it was kind of neat, because there's more efficient algorithms to calculate connected components and so on. So like the breadth-first search and so on. So it's kind of like you might have to do more things. Sometimes the textbook solutions might not work out directly. Okay, so this is about networks. So it's, I think, enough to people to get started with their own project. The other topic the next topic I want to cover is working with text. And in order to work with text, well, that's very interesting. I have no idea why. Maybe from this one I can do it. Let's see. Okay, no password. Okay, so the next notebook that I'll go through is called Web Scraping and Text Mining. And here I just kind of want to get you started a little bit working with text data. And I combine it with web scraping because in many cases you get text data from the web. So it kind of goes together often. So what is the data we are going to work with? Well, I decided to work with the data from the abstracts of the PyData conference. So basically we have this website, right? And we have all the talks, and each talk, if you click on a link, you get information, you have a description, and you have an abstract. So and there is some text in the abstract. So basically, I wanted to learn what is this PyData conference about, based on the topics that we have, or like we can look at the conference from a previous year and kind of learn about something about it. Okay, so in order to get that data, what kind of steps we need to do? So you see that there is one website, and then each one goes to, and somebody doesn't have an abstract, so we'll have like an empty text. So in order to do that, so before we even get to the text, we need to pretty much find all these talks, right, in this website. And then for each talk, we need to go and grab the abstract from that other website, right? So for this, we need to do a little bit of web scraping, but why not? It's not too hard. So let's go through the steps for it. So there's two packages that pretty much you need in order to deal with the web stuff. So one of them is URL lib, and this particular package, kind of the commands change between Python 2 and Python 3. So if you have Python 2, you'll have to adjust a little bit this notebook to make it work. But basically, this gets you information from links on the web. And the other package is called Beautiful Soup, which pretty much scrapes the whole website and gets you information from the website. So they together kind of give you everything you need. So all right, so first, it's kind of the first step is to get this, pretty much get the information from this schedule website. And if we do that, let me split these. If we do that, we get this object. Oh, have a problem because we didn't import things. So basically, it gives us the, because I said to read, it gives us like an HTML of the website with a lot of different stuff. So I'm not a web developer, but you can recognize some things that, you know, like there's like a header and so on. Okay, so then to kind of organize this ugly soup to a beautiful soup, you use this Beautiful Soup package, which pretty much reads this, kind of reads this web page, but organizes things by their corresponding tags. So I don't know all the details about it, but like the idea is that it's just a little bit more organized version of the original page. So okay, so let's look at what this thing is. So this schedule, it's, in terms of type, it's a special type. So it doesn't give us much information. It's some sort of Beautiful Soup type of object. But the important thing is that we can use the find command to find things in this object. Okay, so let's go, and we have something very specific in mind that we want. For example, in this case, if we look at all the href links, we find pretty much all the links in this website. And we scroll down and we see there are like some of the venue links and so on. But the ones we're interested in is the one that says schedule, presentation, and some number. So these are all the presentations, right? So we know that we want only those to get to the links of the talks. So I just kind of add this extra condition that I want to grab all the ones that are a link if there is this schedule presentation in that link. So, and these are the ones I want. So I use a list comprehension which just makes things shorter but sometimes less clear. But the idea is that it's still readable intuitively, right? Intuitively, we want all of these if that is inside the link. And I added the beginning of the website, which is pydata.org, so that I have the whole link. Okay? So with that line, we should get all the links. So we get all the links now, right? Okay. So as you see, this from the front website, you don't really know what you're looking for. You had to kind of dig into these things to see that this is the thing that it's going to involve schedule presentation. So in a sense, it involves a little bit of like looking into it, but then you can kind of grab what you need. All right, so we have this list of links now. So for each link now, we want the abstract. So we're going to do the same thing we did before, that we're going to first use the URL open to open that link. So this is just the first link, for example. And then I'm going to use the beautiful soup to organize things in that link. So let's look at this. Actually, let's split them again. So talk web page is again an ugly HTML document, and then we can parse it with beautiful soup. So what do we need now? Like if we kind of scroll here somewhere, actually don't know where, but somewhere here, so here there is this statement which starts class abstract, and then after that the abstract follows. So this is kind of the indicator to tell us where the abstract is. I mean, I had to look at it to figure it out. I didn't know in advance because I didn't know how they wrote the web page. But now that I have that, I can pretty much grab this whole kind of object with the text. So how do we do that? Well, we specify that we want this div class that's called abstract, and we also want to just get the text from it. So that's all. So let's do that, and then we look at it, and we just get the text from it. So for every class, you can specify the class and the name, and you can get the text corresponding to that part of the website. Okay, so now we have actual text that we can work with. Okay, so what do we do with text? When we get text, you still see that there's like there is some end lines, and you might need to do a little bit of pre-processing before you start working. So there are a few steps that are very typical when working with text that usually people do. Depends on the task, but people often do. So NLTK is one of the most popular natural language toolboxes in Python. And in order to use that, you can first run import NLTK. So it's part of Anaconda, so you should have it working. But what's not there, it's not, if you haven't used it before, you don't have any, so in order to use these toolboxes, you need some sort of like dictionary somewhere to tell you every time you do something with text to kind of check in that dictionary what's a word and what's not a word, or so on. So in order to get those, if you haven't done it before, you can run this command nltk download, and it should open a window which in my case now I run it before that, so everything is installed. But if you haven't done it before, you can go and install them so that you have them in the future. And they take some space. If you don't have space, I think this is sufficient, all NLTK. So you don't have to run them all. If you want to have them for the future, you can run them, but figure out whether you have enough space on your laptop. So then you click download here, and you'll have, in the future, you'll have it, and you won't need to run this anymore. So it's just like a first step thing. So this is basically, these are these corpora, which contain the information for the English language or for some other language. And it has information about what's a verb, what's a pronoun, and so on. So much more than just some sort of strings. Okay, so we close this, and it might take a little bit of time to download it, so just because it's a whole language. So in my case, I already have them, so I can start using them. And so one of the typical steps to start with is to sort of get this abstract, which is just a long string right now. It's a string, and convert it to some sort of words, which are called kind of like meaningful objects, which are called tokens. So in order to do that, there are different tokenizers to use, and one of them is called the regEx, regular expression tokenizer. And you can basically pick that one. And there are other tokenizers, there's slight details, but the idea is to convert the string to some sort of meaningful objects, and that Python can understand how to work with. So if you do that, we'll use this regEx tokenizer, and we'll convert the abstract into tokens. And what are tokens? Well, in some sense, these are the words, but there are details about, it's not just splitting by space. It's doing a little bit more than that. But anyway, we have now some sort of a split abstract. So what else we should do is, because if we want to compare to other abstracts, we should synchronize. It doesn't really matter whether something is capitalized or not. It's the same word, right? So that's why it's usually useful to convert all the tokens to lowercase. So this is kind of like a typical step to do. So with this lower command, which is just a command for a string, we can convert all the tokens to lowercase tokens. So we got them lowercased. Okay, what else can we do? We can remove the stop words. So that's where the corpus is helping, because it tells us what are the stop words. Well, so here there is just what are the stop words. Let's look at them. So these are the stop words in this corpus. I actually don't know what is the official definition of a stop word, but there's a lot of pronouns and so on. So let's remove those, because maybe they're not that meaningful. It depends what you want, but in this case, I don't think it matters. So basically, with this one line, we say that we want all the lower tokens if they are not in the stop words. So we'll eliminate the stop words. Okay. And the last step that is usually useful, and I think there are a lot more, I just give you a few examples, is to stem the words. And the reason is that if you have like dancing or dance, doesn't matter who like what. It might be important whether it's dancing now or dance before, but in this case, most probably we just want to know that it's something about dancing. So it doesn't really matter what the ending is, so we care about the root. So that's why we get, usually when we want to do some text processing, we stamp the text so that we just get the roots, which sometimes becomes like, I'll show you that when we do that here, sometimes it's hard to guess even what they came from. So let's look at them. Some of them are okay, but some of them become so short that, well, these are sort of okay. Like memory, I guess. So yeah, some of them become very short. So it's a little bit harder to guess later on what the word was. But it's kind of usually the right approach.
Could you control the stemming process? Could you specify a basis for doing for deriving the stems?
Yeah, I think there are these, so in this case we use this Lancaster procedure or method, but there are other ones, and I actually don't know, I guess there are different rules how to do that. And this is just one of them, Lancaster, and they have names like the different methods. So yeah, I guess using a different method, you get slightly different results. So I think depending on the application, this application, I think of it more like, oh, let's learn about the topics. So it doesn't matter so much. But if it's something you want to learn more about the type of language that they're speaking or something like that, most probably it's important. Okay, so these are like a few steps. There could be more steps to add in, but it's just the idea is that we have to do some pre-processing sometimes. Okay, so the next step is like basically is to organize these, and this we did on one abstract, but we have like I think like 60 abstracts to do it on. So the idea is to put these in a function so that it's easy to apply it to any abstract. And I think it's pretty easy. I actually have the answer after that. I mean, it's nothing. I think the main point is to kind of pay attention to the steps that you have and add the functions that you want. So basically, we create this function. So pretty much by copying and pasting the previous steps, you create this function. You can kind of do it for yourself, but it's really nothing there. I just copied, pasted the previous commands and put them into a function so that it's easy to apply to every abstract. So it's like my pre-processing function. Okay. So once we have that, we can apply it to every abstract. So basically, I made a function that it works on a URL because I had a whole list of URLs. So now I can apply this pre-processing to every link. So if I do that, I mean, basically I can write a for loop to do that, but I'm using these comprehensions just because I felt like using them. But the main point is we apply this function to every URL in the list. Okay, so we should run this first. And that takes time actually because it needs to do stuff, right? So I don't know how long it takes, but the idea is that, so in the end what we're gonna get is we're gonna get a list of lists because we had, for each abstract, we had all these tokens, and so the tokens were a list by themselves. So that's what our text would look like. So in order to do like kind of learn something like summary statistics about what's in the PyData conference, one of the approaches that we can use is to extract some topics from this text, which is a typical approach when you have like a bunch of documents and you want to learn something about it. the individual words might not mean that much, but you want to find common themes from these words. So this is a standard technique, and it relies on some sort of counts. Basically, so like here we get, as I said, we have 65 abstract. Each one consists of these words in some sense. So we can think that if we want to represent the text numerically so that we can do some math on it, or like statistics, we can kind of look at the histogram, right? And we can see which words appear more often and which words appear less often, and so on. So basically, this can give us a lot of information for each document by getting a histogram of the words, so like the word counts. And on the other hand, if we see that the word appears very often in a text, like data, for example, but if this word appears in every of the abstracts, so that's most probably not interesting, because, well, all of them, you know, every abstract is about data, so I don't learn anything specific. So that's why there is the notion of term frequency, which, as I said, is the frequency of each term in a document. But then there is also the inverse document frequency, which pretty much tells you if a word appears often across all documents, then it's not that interesting, so we scale down the weight. So in a sense, we want words that appear a lot in some documents and are sort of unique also to these documents. So that's kind of the idea. So if we build such an object, then we can kind of do some operations on it to get the topics. So this is like a typical, basically this is a standard approach to build this term frequency inverse document frequency matrix. And from then you can do a lot of things with it. So you can actually do it yourself. So I actually encourage you as an exercise to try and build such a matrix yourself. But Python has some ways to do it for you. But I think it's useful to actually try to create one for yourself. So in order to use the Python ones, though, it's a little bit, I think there is a way around it, but in this case, I had to go back to strings again, right? You remember we converted the text to tokens. We stamped everything, and we got a list of tokens. But in order to use the counting functions in Python, I had to go back to string again, which is basically what these few steps are doing. So it's really not, don't ponder too much on it. It's basically converting back to string. And I think there is a way to avoid that. So I'm sure somebody can figure out another function. But the function that I wanted to use, which is basically this TF IDF vectorizer, required a string again, so I had to go back to string. Does make sense? It was more of a like Python details. So I want you to try. I think maybe I'll give you like maybe 5 minutes. I want you to try to do it yourself. I think it's useful exercise. Even if you don't have loaded everything, just try to think a little bit of how you would write a function to do it by yourself, to basically create a matrix of counts for each word. So I guess I should go to this link. So maybe here there's a good example. So pretty much we have all the documents along one line, and we have the joint set of words on the other line. So the joint because there's going to be some words in one document and another set of words in another document, but we want to build sort of the whole language. So the total number here would be the total number of unique words. And we pretty much, first we want to just build like a term frequency matrix, which is just the number of counts. And then we can kind of scale it up to divide by the document frequency. So you can kind of look at the actual definition. But first, I just want you to build the matrix of term frequencies. Don't even worry about the inverse, because that's just a useful exercise. And then we'll just use the Python function, but I just want you to try to see how it works. And then you can even compare the speed. So I'll give you like 5 minutes to play with it. And if you haven't loaded everything, just think of the think how you would write the function, even on paper, just as an exercise. And you can chat with your neighbor if you want to. There are different ways to do that. Hello.
So I've been trying to follow along. I wasn't even able to install the Jupyter notebooks. It looks like it's just not working. So I'm not quite sure what's going on. Do you have any ideas?
So this, so seems you got to somewhere. So seems you're like already, because at least you got these Jupyter stuff. So in a sense, some part of it is there. So can we look at the terminal where you try to run it?
Sure. So it said refusing to serve any directory or port error. Any sense of why?
Oh, it's kind of asking. I actually tried to ask me this about the one-time authentication. What if you follow these steps with this token and just do the steps?
So just copy paste.
Yeah, I think just follow exactly there.
Okay.
I've gotten this sometimes, and I don't know why occasionally it asks me for this token.
I see.
And it's gonna ask you for a token. I'm just gonna put this there, and hopefully that would open the notebooks.
Yeah. And then I installed Anaconda. Sorry. Let's see. Copy. Is this right? I see what you mean.
This was just something with Jupyter version.
Oh, actually, but sorry, this is probably not going to work because I shut down Jupyter, so that's going to fail. Let me try this again. Okay, now it probably might give me a new token, right? Thanks for your help. Very happy. basic question.
No, it started coming up with some newer version. I think once you set it up, you won't need to do that
Right.
at all.
Yeah, it was-
But there's something that when you initially.
I'm sorry?
I'm trying to view this picture.
478. So I'm not sure. I tried installing Anaconda. I had it installed. I was able to open it.
Okay.
And then when I went to, on the upper left corner, it said Start Notebook.
Okay.
So I went there, and it didn't. I started it, and it would just stop.
So I wonder whether that's linked to your. Can you just cut it off? Something I don't know. Like, can you just cut it off? I don't know. Seems like it's not.
Oh yeah. Let's see. There.
Can you run Python? I just want to see what version it kind of runs. Whether it's talking to your Anaconda. Should be the Anaconda one. You don't have another version of Python. Most probably. Oh. Doesn't say Anaconda, but you haven't installed another one before.
I had a version installed before.
Okay, because that's what I'm wondering, whether it's confusing the versions. For the Anaconda, I think if you set up like, there is a way to set up that it becomes your default. And I thought it does it when you just install it.
Okay, maybe I need to reinstall it.
You won't need to reinstall it. I think just maybe check. I think there is like something to add to your startup path, so that like in your profile, so that it knows that it's which version you want. So you can just Google this, how to do it on Windows. I know how to do it on a Mac and Linux, but I think there is this startup file which is for like settings for paths.
Okay.
And I think you need to just add the Anaconda path there.
Okay.
And hopefully then every time you run Python, you're gonna get the Anaconda one.
I see.
So that
Okay.
it might be confusing the other one.
Yeah, I think when I installed it, maybe I didn't check that box.
Yeah, I think it's like a few things, like do you want this, this?
Right.
But you can set it up after that, so you won't need it to reinstall.
Don't need to reinstall it.
Yeah.
Okay. So you just recommend looking up how to set the path.
Yeah, check that, so to make sure that we get the right version. And that thing should be working, but I don't know. Maybe that would resolve that, I don't know. I'll try first to fix the path. Yeah.
Great. Thanks for your help.
Makes it super.
So what kind of ideas came from the discussion? Anybody actually implemented it or have an idea of how to implement it? There are different ways to do this. I just wonder what kind of approaches people thought of. Or what kind of difficulties you thought you'll encounter if you have to do that. So what if we want to build one row for one document, right? Maybe that's the simplest step first to do. We have one abstract. We want to have, for each word, we want to know the number of times the word appears. How do we do that?
So you would just do like a loop through the tokens and like say like if it and like store it as like so for each token, if it already is in like some separate list, then don't put it in. But so like you would for each token, if it's already in the separate like vector, then you wouldn't put it in, but you would put it as like a count, and then if it does, you would like check it. I don't think I'm voicing what I want to say, but you would want to loop through all of the tokens within that document and keep a count
Yeah, so basically we go through the document. If we see a word for a first time, we set up like a container for it, like it's going to be one row of this matrix. And if we see it again, we add +1. And if we see a new word, we add a new row, something like that, kind of. And we start building the rows.
And then if you like do it for like adding it for different documents, then if there's new terms, then you just add like zeros for those new terms or whatever.
Yeah. So basically, we initiate. I guess we could initiate all the terms initially, like by looking at the joint text from all the documents, like the total, the distinct words that appear. We can use a set for that, right? If we want to get like just the unique elements, we can set the elements, all the tokens, and then set it to 0. And then if we see it, we start adding 1 plus 1 plus 2. So yeah, that's kind of one approach. Any other approaches people thought of, like using sometimes some other libraries? This is kind of like the pure Python approach. Any other ideas? Yes?
You can like define the vector of all the words, and then so it's going to be the same for every document, and then you can just loop through and increment the appropriate index each time the word appears, and then concatenate them together in the matrix.
Okay, so in your case, you set first the vector of all the words, right?
Exactly.
So you fix, so you don't like, otherwise, in your example, you kind of, if you see a new one, you append, right? In your case, you're gonna allocate sort of this vector. So you're just gonna be adding the zeros and ones. So that's kind of the difference. Yeah, that's another approach. So yeah, like I think these are getting to the little details that if these matrices are big, like that, then these things would matter, whether we take one approach or another approach. Like for example, if we can allocate all the memory, then it's better to allocate it in advance. If, on the other hand, if the total number would never fit into our memory, then it's actually better to do the appending approach and kind of do it piece by piece, because the appending can work. As long as you keep on adding things, you don't have to load everything at the same time. So these are kind of different approaches. And I'll add a few more that are more based on, I think they're just based on some, I'll just show you some functions that exist pretty much they exist in Python to do something like that, and they might be useful for other things. So there is something called collections. This is like collections in general, Python collections. So this is just a sub-package. And what does it have? It has named tuple. This is a little bit more general Python thing, but I think it's useful. So it has a named tuple. So if you actually know what a tuple is, named tuple, so tuple doesn't have names. Sometimes you really want to have names. This is named tuple. There is dequeue, something like something that can pop things out. So the one that the reason I'm showing this to you is that there's this thing called counter, and that's kind of useful in this situation when you pretty much do this counting. So this pretty much does what your approaches are suggesting. Like every time you get a new one, it keeps on counting. So you can kind of look back and see how to use it. Anytime you need to do something counting like that, like histograms, you can use this counter container, which is a special container in Python. And let's see if they have an example. I actually don't like their examples, but maybe I'm not reading carefully. Anyway, if you need histogram, use count. So that's like a histogram of the words we need. Use counter and check an example how to use it. I'm not reading carefully, so but that's what it is useful for. So, and I'll just mention this since we're on this page. This is independent. Dictionaries in Python, if you have used them, you know that they don't have order, and that's why they have the properties that they have. They're designed not to have order. But sometimes you really want to have something with an order. They have something called ordered dictionary. So, and you can convert a dictionary into an ordered dictionary. So it's just useful in general, since we're on this collections thing. Okay, so let's get back. So, and I think also another thing is Pandas has a histogram, a histogram function. So, which works with strings, with words. So you can use that. Basically, it's gonna do like a histogram. Because like if you use other functions like from NumPy, they're designed for numerical numbers, so they won't work with the strings. They won't work with the words. But Python has, Pandas has some histogram. So yeah, different approaches. But as I said, Python has a whole function to do this, to build this matrix for you. So you really don't have to do it. I just wanted you to think about how you do it. So, and the functionality is using these, so pretty much now we're jumping into scikit-learn package, which has several functionalities to extract features from text. And one of them is to really build this matrix because it's a famous matrix. So we get this TF-IDF vectorizer, and these details here pretty much tell us whether we want a word to appear at least twice. So you get like a minimum bound. By default is 1, but if you want to set I want this word only if it appears at least twice, then you can set a bound. And if a word appears in 95% of the documents, more than 95% of the documents, you want to use it because it's too popular. So you set some bounds on which words you want. And basically after that, you just apply these fit transform function to your abstract. So basically, there's a lot of like names here, but the main point is that we import this package, we initialize it, and need to run that before that. And we get the matrix. So, and you see that the matrix is sparse, which is good because in general you want to store these. Usually you won't have the same words in all the text, so you have a lot of zeros. So like not the same words appear in all the documents, but the dictionary is big. So, so you want a sparse matrix so that you can manipulate it better. Okay, and in this case it's not that big, it's 65 documents, so I guess 587 words. So our dictionary is really small. Okay, so now back to some linear algebra. And again, just getting this matrix, we can do manipulations on the matrix and get interesting information just by applying some transformation. So the method that I'll go through is called non-negative matrix factorization, and it's one of the popular approaches to find topics. The idea is that we just want to take this matrix and split it into topics and weights. So basically we decompose the matrix into a linear combination of topics. So you can read more about the math behind it, but I'll just show you how to use it now and see what we get out of it. So okay, so in this case I set the number of topics to 5. The number matters in a sense that if you run 5 and if you run 4, clearly you'll get one more topic, but you'll also get different topics. So keep this in mind. The number matters a lot. It's not like nested. So anyway, I picked 5 and I import NMF from scikit-learn decomposition package. If you've used scikit-learn before, you might have can split this. If you use it, you might have used a PCA from it. It's a pretty popular approach, principal component analysis. But together with PCA, there's a lot of other functions, and one of them is NMF. And the reason we want NMF is because we want the weights to be positive so that they represent some sort of probability of being from this topic or that topic. So there's a lot of details behind it and kind of interpretation, but I'll just show you how to do that. So okay, so we import NMF, and there's some initialization, doesn't matter so much, or you don't even need to set it. You can use the default ones. And then you just get the two matrices, which one is corresponding to weights, the other one is corresponding to topics in some sense. So we just run it like this. So let me show you now what these objects are that we got in terms of dimensions. So the shape of the W matrix is 65 and 5, and the shape of the H matrix is 5 and 587. So what these mean are like, so we have 5 topics, and we can represent, pretty much we can represent each document with these 5 topics. So these would be the weights for, so the first matrix, 65 is the number of documents, and so basically you get weights for each document for the individual topics. So you can represent each document through the topics on one hand. On the other hand, you can represent each topic with all the words, so depending on what words you get here. So basically it gives you representation of the topics on one hand and of how the documents are represented with these topics. So as I said, you can read more about it, but it's important to look at the dimensions because they tell you which matrix is which. Okay, so the H contains the topics, and kind of the last statement, pretty much what it does is that it takes the first 10 words for each topic and it just displays them. And based on those words, we try to guess, oh, what's this topic? So we call it topic, but the truth is it might not be that meaningful. So let's run that. And as I said, it's just doing some sorting and extracting 10 words for each topic. Nothing much more than that. So these are the topics that we got. And I looked at them, and I cannot say what they mean. So that's good, because that means that we need to improve this method. Because I looked at them, and kind of the idea was to just guess. First I thought, oh, this is maybe more statistical, covariances, forecasting, costs. But then we got hardware. So yeah, I don't know. So these are the topics of PyData conference. I guess it's just everything is so diverse that we can talk about everything at the same time. We don't need one topic. So yeah, I mean, anyway, this is kind of like just an exercise. I just wanted to use that data set. And you can actually play with it and try to you can play with the number of components. You can play with the pre-processing part. Maybe you remove some words that don't matter and so on. So maybe you can get some meaningful topics out of it. And just a little note to tell you in general, so with abstracts, these are very short documents. So it's much harder to do topic modeling with short documents because usually words appear like 1 or 2 times. I mean, it's a short. It's not like if you have like a whole book on biology, you're gonna get like 5 million biology terms appearing over and over again. So that's why these are the the term frequency approach, it works very well with Wikipedia articles and so on. But you know, these are very short, so it becomes tricky. So you have to think more of what a good approach to do that. Okay, and here I just have a few final things to say about what to do if you have like a lot of documents. This kind of little bit regarding the discussion of how to even calculate these matrices. So the important thing is that everything you do, you can separate document by document when you do these counts, or when you do the pre-processing. You can split it, you can parallelize it, you can run it on different computers. You can share with your roommates. I do one, you do another one, so on. So that's a good thing about this approach. And there are some libraries which can deal with this, like so Dask is a Python library which can do you can do the counting kind of like without loading everything at the same time. And Spark has the mlib library. So Dask and Spark kind of have a similar approach to this. So you can kind of go and explore how to do that. And in this case, you don't have to load everything. Okay, so that's all about text, I have to say. Any questions on the text topic in general, like kind of just dealing with Python and text or web scraping? Yes?
I wondered for this whole like randomly assigning topics thing, is there any way, like if I wanted to do a sweep between like, you know, 2 topics and 20 topics, if I could get some kind of score to see which of those numbers is the best choice?
Yeah, so actually there is another package in Python, which is not part of Anaconda, but it's called Nympha. And one of the goals of Nympha Python, one of the goals of this package is to play with the costs, and pretty much they run this automatically for you. They try to find the optimal number of components. And also, when I say non-negative matrix factorization, there's a lot of different ways to implement it. So they basically focus on comparing all these different ways, different costs. So that's kind of one way to study. There is no one correct solution. So pretty much you test it and you look at the result, and that's kind of the approach to do that. Any other questions? Okay, so we'll jump into the next topic, which is the sound notebook, because I want to introduce you to some sound processing in Python. Okay, so in this case, first I thought I'll grab some kind of like music database, and you know, we'll do something with some music online. The truth is, it's not that simple, and the reason is that, you know, there's the copyright, so you can't just grab some database of music, and usually they have features of the songs, but they don't have the raw songs. And there are some databases which you can access the raw data, but it was in another format. So anyway, so that led me to use a bird sounds database, because bird sounds don't have a copyright, I guess. I mean, they have a copyright, but it's not that restrictive. So there is this website, which is kind of interesting. It's called Xenocounto, where people, it's like crowdsourcing website in which people record sounds of birds and they upload them, and then people like annotate them and so on. So you have like a lot of recordings of bird songs. And from that website, there is another data set which it's a little bit hard to get data in bulk from it. So anyway, there is another data set that somebody shared, and I used, and you can kind of download it for yourself if you want to play. So it's basically just an organized subset of the database. So anyway, it's loading. But there is a link to the data set that I'll be using. So pretty much this is just a subset some people kind of annotated and saved and put on Zenodo. And you can download it as long as and cite it the way they ask you to cite it. and use their license. Okay, so anyway, I downloaded it, and there's like a bunch of .wave WAV files, which are music files there, and the idea is just to read them and play with them in Python. Okay, so first we just run these standard packages. In order to read a .wav file in Python, one of the simplest way to do it is to use the scipy.io package, which has a lot of I/O, like input, output, read different formats, and one of them is the WAV. I don't know how to pronounce it. The WAV wave extension. Anyway, interestingly, you don't have MP3, and the reason is that MP3 has its own licensing, like kind of like conditions. So when they try to merge it with other packages, like which are have a more user-friendly license, they don't work together. So you'll find that a lot of things, a lot of like standard packages in Anaconda don't have MP3 and MP4 functionality just because of the licensing details. But anyway, these are not MP3, so we can directly read them using the WAV file read function. So let's run this. And in terms of format, it's pretty simple. So I stored it into something called bird sound, and it has two things in it. You see that kind of the length is 2. It contains 2 elements. One of them is just, the first element is just the frequency. And the second element is basically the signal. So it's pretty simple representation. From then on, you can kind of do, you get it into like Python, and you can do whatever you want with it. You don't have to worry about the format. And just one note that in this case, these have only one channel, but sometimes you can have like, depending on the camera, you can have a multi-channel signal. So you'll have, instead of one-dimensional thing here, you'll have a multi-dimensional kind of object. So you have more channels. So just keep this in mind, but otherwise it's pretty simple. So okay, so it's just one-dimensional. So we can actually plot it. Let's just do that here. So that's what it is. This is the sound of the song. And in this case, when I plot it, you can see that the axis, the time axis is kind of off because it's just showing the frame in the signal, which is not nice, right? You want to show the true time. So in order to do that, you can use the frequency to adjust it. So in this case, bird sound 0 is the frequency, the first element. And then you can pretty much divide the frame number by the frequency to get a real time. So, and then you get something like that, and that's now seconds, so you know the real time, 7 seconds, something like that. Okay, so this is what the signal is. You can read it now. You can actually play it, which is kind of neat. So this is using the IPython display functionality. So you just import this thing, and we can run it if it works. Okay. So I listened to this while preparing this, and then I started hearing the same sound everywhere, like all the time. And I don't even know which type it is, but you don't hear it until there's like, I'm pretty sure it's the same one. So okay, so that's how you deal with sound. And you see that, in general, when you work with sound, the signals are, you have to do a little bit, like sometimes standard methods don't work because you have these like up and downs, and like the frequency matters, not just the amplitude. So you have to do a little bit more. So usually what people do is, apart from looking at the sound, they also look at the spectrogram. So the spectrogram is basically, what it does is, I'll just show you the picture first and recall what it is. So what it does is it looks at these, first of all, it looks at all different frequencies and calculates like a windowed Fourier transform. So in the end, you get this kind of, in some sense, like a 2D representation of the signal, which usually it's more informative than just the 1D representation. And the good thing is that because it's kind of like an image, you can kind of see patterns and you can extract, it's kind of like people, a lot of these people who actually study birds, they can look at the spectrum and they know which bird is by the pattern that they get. So they know which bird it is, which I think it's harder just from the signal. So in this case, you can kind of like, in terms of approaches of dealing with sound, you can work directly with the sound, but in many cases, you can just go ahead and start working with the spectrogram and extract features from the spectrogram, instead extracting features from the sound, and do some analysis on it. So in some sense, you might need to do image processing without really having real images. So that's one of the main points I kind of wanted to make, that you never know when you need what. So it might as well learn how to do these things. And you might just get data that looks like that. Okay, so I'll say like just a few things regarding that. I won't get too much into the features that people extract. You can read more about this in general. Like it depends really on your problem and what you try to do. But one of the important things is that when you have sound, is that first, well, let's look at an example. So let's just plot I want to plot two different things. So this is song 1. Let's try to get another one. I just want to get 2 signals. So let's do 2. So let's just plot these 2 ones. So these come, I think, from the same species. Oh, okay, so I need to look at the second element. So remember, it was just the second element was the signal. So let's do that. So okay, so these are 2 different songs. But as you see, in reality, one of them is just, I think it's like around 1 second. The other one is like the whole sequence. So, if you try to do some analysis on these, kind of like on these songs, well, first of all, they're different dimension, right? They're different length. They might not be aligned. I mean, pretty much you don't know whether this corresponds to this part or this part or this part. So the idea is that there are some things that you have to do that you don't do normally when you work with other data sets. So basically regarding like the time alignment and so on. So one way to approach this is to in some sense search for patterns, like in this case this is just one chunk, and try to find the best pattern to fit this into this song and see whether they have like some overlap or not. So let's look at some example. So So in this case, I automated the reading of the files using this glob function. You can look at it later on, but the main point is to extract all the songs for all the files in the folder. And those are drumming. We can listen to one drumming. Let's do that. So that's the drumming, just for fun. Anyway, so the drumming, their signal looks like this. So these are two different ones, and I plot them together, and you see the pattern is kind of similar, but they are just not aligned. And I don't know whether it's easy to distinguish birds just by their drumming. Actually, I don't know that. But anyway, the point is that if I want to compare these two sounds, and I want to see whether they're the same or from the same bird or something like that, I first need to do something to make sure that this pattern gets aligned. And does anybody remember how to do that? There's one approach to try to adjust this. What kind of ideas you have? So cross-correlation, right? So basically, here there is like a mismatch. If we can calculate the correlation between all the values, hopefully at some it's going to be maximum at some point. So the main idea is that you calculate for different lags. So if you think of covariance, you just calculate it. For one signal, you square everything. But for cross-correlation, you take one signal and you keep on moving it and multiply the values. And at some lag, they're going to match. So that's kind of the idea, conceptually. And so if we find at what shift we get the maximum correlation, we can just shift it and align them. In order to do that, in Python, there is actually a NP correlate function, but I don't think that it's, I have to check that, but I think it's not the most efficient way to do it. And the most efficient way to do it is to use Fourier transforms. And this is kind of another like a little trick to remember from school, that you can actually get cross-correlation only by Fourier transforms. So I won't get into the details, but pretty much if you reverse the signal, one of the signals, and you calculate and you convolve those two signals, you'll get the cross-correlation, some trick like that. Anyway, so the main point is we can do it, and here are the steps to do it with a few details, because you need to pretty much, you have one song, you have another song reversed, and there are some details of how to deal with the boundaries. So, and then because of that, you need to do you kind of find the maximum correlation, but you need to adjust because they're of different length. So you can check the details later, but the main point is that there is a step to do it. There is an approach to do that. And if we do it with Fourier transforms, it's going to be efficient, or as efficient as it can get. Okay, so let's just do that. So we get some offset, and in this case we got negative offset. So this means that I have to move. I guess I have to move I need to move the first one backwards. But because I cannot move the first one backwards in terms of indices, I move the second one forward, something like that. So okay, so they kind of got sort of aligned, and I don't claim that this is the best we can achieve. And one note is about this approach that it only looks at linear shifts. So if there is some stretching, that's not going to work. So you have to think of other ways to do that. There are ways to warp the signals to match them and so on. So there's a lot of things to do, but the main point is that you have to do, when you work with sound, you have to do a few extra steps to get to the point of doing the things you know how to do. And for this one, like I think once you kind of align them, you can kind of now calculate some distances between them, and kind of based on the approach from the first discussion, once we have distances, we can actually build a network, and we can study similarities, clusters, and so on. And this way we can actually cluster the different species. So, so basically you can, once you get to that point, you can use the same approaches as of the first part. Okay. So here I have some general questions of how you can do that. And it's open at this point, like, because you can do this on the signal, but you can also shift the spectrograms and align the spectrograms instead. So there's a lot of possibilities. Okay, in the last few minutes, I'll just show you one more example, and I'll stop. So the last example we have is to work with video, just for a difference. So I have a very short notebook in which I have only one video, and I'll show you. Let me see if I can show you the video. So this was just something I shot on campus when we had the cherry blossoms. And you know how you want to get the picture of everything, of the background, and all these people are in front of you. So the question is, how do we extract from this video the background? Because I just want the picture of the cherries. So it's a simple computer vision problem. Okay, so let's do that quickly. So we have a video, and as I said, there's a little bit of a trouble with MP3s and MP4s. And to the best of my knowledge, I don't think there is a way just with pure Anaconda to read MP4. You need to install extra packages, unfortunately. So there is a way to read TIFF files if you have sequences of images. But if your videos come from the camera, they won't be TIFF. So you have to install some extra stuff. So one package that is pretty light, and I like, although it's not the most efficient one, is called Image.io. And you can install it using the conda install command, so it's nothing too bad. It's just you need to make the extra step. And that package might require another package which is super powerful when working with videos. It's called FFmpeg. And if you don't have it, there is a step to do so that it can download it on your computer. And I'm saying here, like, once you get to FFmpeg, it a little bit depends on your system, so that's why there's always issues with dependencies. So it's a little bit harder to develop Python code for videos because there's always these troubles with these library dependencies. So keep this in mind, but I think this is one clean approach to do it, that first install Image.io and then set up FFmpeg through Image.io. It's kind of like a trick, otherwise you need to install things separately. Okay, I have it set up on my computer, so I have an advantage, but I hope it works for you with these steps too. But in my case, I already have it, and I have the video. So I just go through the steps, and when Image.io, kind of like the first step is to get this sort of link to the video. It doesn't do anything, it doesn't read it, because reading a whole video, it's expensive. But this is a way to set a link to the video, and then you can decide which frames you want. And in this case, for example, if I want to just get the first frame, I just do get data, and I display the first frame. You can go further and so on. But in our case, I want to read the whole video, but I won't read the whole one because it's kind of expensive. So I'll skip like every 50 frames and try to do something with that, because even one video, it becomes it becomes trouble to work with it. Okay, so I'll read that, and I do a few steps while reading it. I'll just show you. So I just decided to take the first channel. So the video is like a kind of pixels, row pixels, column pixels, and 3 colors. But I just take the first color just to make it smaller. And this function ravel, it just makes it a long vector. So all I'm doing it, I'm reading the video as a long vector. And so because I read it as a long vector, the shape of this final thing is, so 50 is the number of frames I'm reading, and this is the total number of pixels in a frame. Okay, so now I just have a matrix, and I'll apply the same method that we apply on the text, and I'll apply it on the video. And I claim that if I do that, I can actually extract the background. So I'll apply non-negative matrix factorization on this matrix. It's positive, why not? Let's decompose it. And I set the number of components to 1 because in this case I just want the background. I don't really care about other kind of components. I just want to get the background. So I set that and pretty much run the same steps that we did before, like in the previous example. And that would take time because now it's much bigger. So it would take even more time if we had the full video. So these things start to become very expensive. And once it's finished, it's gonna show the result. But yeah, I can say a few words about what to do when there is no space. So in general, like now videos are getting bigger and bigger. They're like 4K, whatever. That causes trouble like working with them. Even one of them cannot fit into RAM. So some approaches to deal with that is, so there's something called in Python memory mapping, which kind of creates, this is for any NumPy array. It stores it on the disk, and then you can have access to every frame from disk. So it takes more space, but it's very efficient if you want the 3rd frame, the 20th frame. So if you want to access your video very often, you first store it into this memory mapped object, and then you can access it. So HDF5 is another format which is kind of doing something similar, but it's more general. It's not just for Python. So people know it, you can transfer it from one place to another. Main point is you can access frames independently. You don't have to read. Actually, for what we are doing now, in order to get to the whatever frame, I have to read. I have to search for it, so it's kind of slow. So, and as I mentioned before, there's the Dask library which uses bags when it works with text. But if you want to work with images, you have something called Dask array, which is pretty much the same idea as memory map and HDF5 kind of. You can parallelize things and store things on the disk in some sense. So yeah, I think these are kind of, there is no magic. I mean, if you have GPUs, you can use them, but that requires hardware.
Valentina?
Yes.
We need to move to questions.
So yeah, so that's all I have. This is still running. It's gonna finish at some point. So let me know what kind of questions you have. If you have any questions. Yes.
What's the most best recommended IDE for Python?
It's hard to say. Maybe PyCharm is the best choice. I use Atom, which is just like kind of like editor, which you can add extra packages to it to make it the way you like it. So yeah, I would say either PyCharm or Atom. You can use the notebooks to play around, but they're not very good for development. So yeah.